Okay, so last time we were talking about riffle shuffles, and we gave an upper bound for the mixing time, which was on the order of log n. And so now I'm going to give a lower bound, which will also be on the order of log n, and this will be just using a counting bound. So let's say we fix some epsilon between 0 and 1, then the mixing time of the riffle shuffle on a deck of n cards satisfies the T mix of epsilon is at least 1 minus little o of 1 log base 2 of n. Okay, and then the proof is to use a counting bound. So I'll say the maximum out degree of a state, and by that I mean if you're looking at the transition diagram of the Markov chain, this is just like the maximum number of arrows going out from some state. This is the state is what we called delta earlier, and this is 2 to the n, right? Because there are like 2 to the n ways that you can split it into 2 decks and then shuffle them, like, riffle them together. And so, if you just go back to, we had some simple counting bound coming from this, where we said T mix of epsilon is at least log of size of the state space, 1 minus epsilon, divided by the log of delta. Okay, well this is log of 1 minus epsilon times n factorial over log of delta, and log of delta, okay, so that's log of 2 to the n, so that's just in log 2. And okay, what is this? Well, by Stirling's, okay, so log of 1 minus epsilon in factorial is just log of 1 minus epsilon plus log of n factorial. Log of n factorial is on the order of n log n. Right, so we get like 1 minus, so this is like n log n over n log 2. So this is going to be log n over log 2, which is log base 2 of n, which is what we want. And then there's like a 1 minus little o of 1 coming from the approximation. Okay. So I do want to talk more about shuffling, but I think for that I'm going to need to talk about spectral methods, which are interesting by themselves. So I'm going to do sort of a detour talking about spectral methods, where we're going to look at like eigenvalues of the transition matrix. That'll tell us things about mixing, and then maybe later we'll come back to doing more shuffling stuff. And before I talk about spectral methods, I need one thing that I skipped over from the book. I don't really want to spend too much time on it, but it's something that I'll just need, so I'll sort of state something and not really prove it. So if we have some p between 1 and infinity, some real number, and some function f from our state space to the reals, we can consider the p norm of f. So this is this f norm sub p, which is going to be, well, okay, let me split it into two cases. If p is finite, this is what you get by taking the sum over all y in the state space of f of y to the p, but I want to weight it by the stationary distribution pi of y. So our norm will be with respect to this stationary probability distribution, and then I want to take this to the power of 1 over p, and this is if p is finite. And then if p is infinite, then this is just going to be the max over y in x of f of y. Okay. Okay, and I also want to let, so I'll define this inner product f comma g sub pi, and this will just be sort of a typical inner product formula, sum over x and x of f of x. So here f and g are two functions from our state space to the reals, so I'm just going to take f of x, g of x, but again I'm going to weight this by pi of x as well. And, okay, so we have this inner product depending on pi, and I'm going to let q sub t of xy be p to the t of xy divided by pi of y. Okay, so this is something we'll need. Okay, so the probability of going from x to y in t steps times or divided by the stationary probability of y. And I also need to define this dp of t. So this is going to be some kind of analog of our d of t from before. So this will be the maximum over all states x and x of this qt of x dot wait, one second. Oh yeah, minus 1 sub p. Okay, so this is some function from the state space to the reals. If you plug in, right, you can plug in some state here, and that gives you some real number. So then this is some function, and you can take the p norm, and so this is going to be some quantity, and I'm going to state a couple things that are okay. They're proven in the book. I don't really want to prove them here because I don't want to get sort of lost in technical things, and I'd rather talk about more Markov chains and spectral stuff. So I'll just state these, and then we'll sort of just assume they're true. Okay, so one can show that, first of all, okay, I'll call this like diamond. 2 d of t, this quantity that we care about for the mixing time, is the same as d1 of t, if p is 1, and this is less than or equal to d p, which is less than or equal to d infinity of t. Also, if we have a reversible Markov chain, so if p is reversible, then I'll call this diamond. In this case, d infinity of 2t is d2 of t squared. And this is also the max over all states x of q sub 2t of xx minus 1. Okay, so these are just some, I guess, inequalities, identities relating these various dp of t things. And I'll use some of them in a minute. Okay. Okay, so now I'll talk about spectral methods. Okay, so what is the goal of this? We want to understand the mixing of our Markov chain using eigenvalues and eigenfunctions Okay, and so eigenfunction, it's really just the same as eigenvector. So the point is that sometimes I'll think of like f as a function from the state space to the reals, but you could also just think of that as like a vector where the entries in the vector are indexed by the elements of the state space, and this makes sense because our transition matrix P has its rows and columns also indexed by the elements of the state space. So we could call it an eigenfunction if we want to think of it as like a function. You could also call it an eigenvector. Doesn't matter. Eigenvectors of P. Okay. Okay, so I'm also going to state another lemma that I won't prove. Okay, so for this lemma, first, if we have some eigenvalue lambda, so if lambda is an eigenvalue of the transition matrix, then its absolute value is at most 1. Two, if P, so if our transition matrix P is irreducible, then we can look at the space of eigenfunctions with eigenvalue 1. This is like the eigenspace for the eigenvalue 1. Okay, space of eigenfunctions corresponding to eigenvalue 1. And the claim is that this, in the case when P is irreducible, this is one-dimensional. And it's generated by the column vector with all ones. Right, so the point is, it's a, well, why is this an eigenvector with eigenvalue 1? It's because we have a stochastic matrix, so all the rows sum up to 1. So if you just do P applied to this, then you're going to get all ones. So it's an eigenvector of eigenvalue 1. Okay, and then 3, if P is irreducible and aperiodic, then -1 is not an eigenvalue of P. Okay. So I won't prove this, but okay. Oh, I guess I have this inner product. I guess I should also just define like a usual inner product without the pi. So we'll also let like this without the pi subscript be the usual inner product on r to the x, so functions from x to r. And this is just given by like the same formula, but without the pi. Okay. So okay, so for this lemma, now let's suppose, and this I'll actually prove. Okay, let's suppose that P, our transition matrix, is reversible with respect to the stationary distribution pi. Okay, then a few claims. One is that we can look at the inner product space where we look at functions from x to r with this inner product using the pi. Okay, so this inner product space has an orthonormal basis. Orthonormal basis of real valued eigenfunctions Fj, j going from 1 to the size of x, and these correspond to some real eigenvalues corresponding to some real eigenvalues lambda j, j going from 1 to the size of x. Okay, 2. Okay, so the eigenfunction we can assume that the eigenfunction f1, what we're calling here f1, corresponds to the eigenvalue lambda 1, which will be 1. Okay, so this, oh wait, sorry, this is, yeah, sorry, let me not do this one yet. Okay, so for the second one, we have, I just got them out of order. P to the t of xy over pi of y. So this is what we were calling is qt of xy. This is going to be the sum from j equals 1 to the size of x of fj of x, fj of y, lambda j to the t. So we can decompose this quantity in this nice way using these eigenfunctions. Okay, and then the third one, which I was writing earlier, is the eigenfunction f1 corresponding to lambda 1, which we'll take to be 1, can be taken to be the vector, I guess I'll call this like math bb1, and this will be the all ones vector. Okay, like we have some freedom in choosing what this eigenfunction should be, but let's just choose it to be the all ones vector, which is the same we can do. And then if we do this, then we can rewrite this a little bit. We have this, yeah, so this, hold on. Yeah, qt of x y, let's say minus 1, right? So I can pull out the j equals 1 term. If I do that, then what is the j equals 1 term? It's just going to be like 1 times 1 times 1 to the t, so it's just 1. So then I'll subtract that here, and I'm left with the sum over j at least 2. All I'm saying is the first term here is 1, and so I can subtract it, and I get this. Okay. Okay, so for the proof, okay, let's let A, so A is going to be a matrix with rows and columns indexed by the states in our state space. So I'll say that A of xy is pi of x to the 1/2. Is this right? Let me just double check this. Yep, okay. So pi of x to the 1/2, pi of y to the negative 1/2, p of xy. Okay, so the reversibility so we're assuming that P is reversible here. So the reversibility of the chain implies that this matrix A is symmetric. Yeah, so if you just write out what it means to be reversible, it ends up saying exactly that A of xy equals A of yx. Okay, so then we can just use the spectral theorem for symmetric matrices. So by the spectral theorem for symmetric matrices, if we look at the inner product space, of r to the x with this usual inner product without the pi, this has an orthonormal basis of eigenfunctions, eigenvectors. Okay, so an orthonormal of well, okay, I'll say an orthonormal basis, say phi j running from 1 to the size of x, where phi j is an eigenfunction or eigenvector of A, with some real eigenvalue lambda. Lambda j. Okay, so the point is that like we started with P, which was not really a symmetric matrix, but it's kind of like a symmetric matrix. This reversibility is sort of like a quasi version of being symmetric with this pi coming in. So this is just saying that if you change P accordingly by multiplying by pi of x to the 1/2, pi of y to the -1/2, then you actually get a symmetric matrix. Then you can use the spectral theorem from linear algebra, which gives you this orthonormal basis, and then we'll just convert that back into an orthonormal basis of eigenfunctions for P. So, so one can check that square root of pi, okay, by square root of pi I mean it's the function, like this is a function in r to the x that sends an element, let's say y, to like the square root of pi of y. So this is okay, in r to the x. This is an eigenfunction for A with eigenvalue 1. Okay, so then that means we can let phi 1 be this square root of pi and take lambda 1 to be 1. Okay, let's let d sub pi be the diagonal matrix with, well, its entry in position xx should be just pi of x. Okay, well then we can write the relationship between A and P just using this diagonal matrix as then A is d pi to the 1/2 times P times d pi to the -1/2. Okay, so let's let Fj be d pi to the -1/2 phi j. The point is we have this eigenfunction phi j for the matrix A, but now we'll just convert it back into an eigenfunction for P by multiplying by this d pi to the -1/2. Okay, so then Fj is an eigenfunction of P with eigenvalue lambda j. Okay, we can even, let me just write that down. So indeed, we can do the computation. So I can take P Fj, and I want this to be lambda j times Fj. So this should be P d pi to the -1/2 phi j by the definition of Fj. And then this, well, okay, I can write that as d pi to the -1/2 times d pi to the 1/2 P d pi to the -1/2 phi j. Okay, so I didn't really do anything, I just multiplied by d pi to the -1/2, d pi to the 1/2. Okay, but then this is d pi to the -1/2. This is A, and this is still phi j. Phi j is an eigenfunction for A with eigenvalue lambda j, so this is d pi to the -1/2 lambda j phi j, but then I can pull the lambda j out, so I get d pi, so I get lambda j times d pi to the -1/2 phi j, but then that is lambda j fj. Okay. Oh, and I guess also we should check that this collection fj, j going from 1 to the size of x is orthonormal. Orthonormal respect to the inner product with the pi, since, well, okay, this is simple. We just say, if we take fj, or okay, let's take fi and fj, some I and j, with this pi here. Well, okay, you can rewrite the fact that you have the pi, you can rewrite this using like the normal inner product if you put a d pi to the 1/2 in here. Okay, so this is just essentially the definition of the inner product with the pi. Okay, and then, well, this is just the inner product of phi I with phi j, and then that's 0 or 1 depending on if I and j are equal, so it's the Kronecker delta ij. Okay, so this is saying that fi and fj, that the basis here is orthonormal with respect to that inner product. Okay, so we have this orthonormal basis with real eigenvalues, and now we want to check this. So, okay. For some state y in x, let's define let's define delta y. So this will be a function in r to the x by delta y of x is just, well, 0, or it's 1 if y equals x, otherwise it's 0. Okay, then what we can do is expand this function using our orthonormal basis of eigenfunctions. So we have delta y is the sum from j equals 1 to the size of x of this inner product of delta y with fj, with the pi here, times fj. Right, so just because I have an orthonormal basis of eigenfunctions, I can decompose any function by doing this. Okay, and then what is that? Well, then I can just rewrite this as the sum from j equals 1 to the size of x of fj of y, pi of y, fj. Right, so right, this inner product, if you write out what it is, you're just going to get one term when you're summing. Right, you have, where's the definition? What did I write? Oh, this. Right, when you write out the sum, you're just going to have one term where x is y. That's going to give you fj of y and then pi of y. All the other terms are going to be 0. So that's how you get this, and then you still have the fj. And then, okay, yep. And since p to the t fj is lambda j to the t fj, just because fj is an eigenfunction of p with eigenvalue lambda j. And p to the t of xy is, well, you can actually write it as p to the t delta y of x. If you just sort of write out like this what this is, you end up getting that. We have maybe I'll move over here. Okay, so we have p to the t of xy. We can write this as the sum from j equals 1 to the size of x of fj of y pi of y p to the t fj of x. Okay, so that is, yeah, just coming from combining these and using this way of decomposing delta j. We can write this. And then this is equal to sum from j equals 1 to the size of x of fj of y pi of y. This is the same thing, but then this p to the t fj of x is the same as lambda j to the t fj of x. Okay, and then finally, if we divide through by pi of y, then we ended up getting, I think, exactly what we wanted, which was this. Yeah. Yes. So dividing by pi y yields part 2, and then part 3 just follows from part 2 when we take this choice of the eigenfunction with eigenvalue lambda. Okay. So what we're going to want to do, like, I guess the point here is that once you get rid of the like once you subtract the 1 here to to just have the sum using the j's that are at least 2, you really care about, like, okay, what are the sizes of these lambda j's? And so the one that's going to matter is the one that's like the biggest in absolute value among these. So what we'll do is define lambda star. This will be the max of the absolute value of lambda, where lambda is an eigenvalue of p, and lambda is not 1. Okay, so it's the maximum size of an eigenvalue that isn't 1. And then there's this quantity gamma star, which is 1 minus this lambda star. Okay, and this is just, so this is called the absolute spectral gap. Of P. Okay, now when P is reversible, so if P is reversible, then we know that we have actually real eigenvalues. According to this, right, they're actually real eigenvalues, and then we can sort of label them in decreasing order. So in this case, we label the eigenvalues in decreasing order. So 1 is lambda 1, and this is greater than lambda 2, which is greater than or equal to lambda 3, and so on, until lambda sub the size of the state space. This is at least negative 1. Okay, and in this case, just the spectral gap, not the absolute spectral gap, but the spectral gap is just 1 minus lambda 2. Okay, and then one other term, and then we'll say how this relates to mixing time. So the relaxation time of a reversible Markov chain with absolute spectral gap gamma star is, okay, we'll call this T rel, so the relaxation time. This is 1 over gamma star. Okay, and then the point is that we're going to be able to get, so the next theorem is going to give us an upper bound on the mixing time in terms of this relaxation time. So suppose P is reversible, and irreducible. pi min be just the minimum possible value of a stationary probability, so it's the minimum over x and x of pi of x. Then T mix of epsilon is at most the ceiling of the relaxation time times some quantity. This is 1/2 log of 1 over pi min plus log of 1 over 2 epsilon. Okay. Okay, so let's prove this. Okay, so we're going to use Cauchy-Schwarz. So by the Cauchy-Schwarz inequality, okay, we can write the absolute value of p to the t of xy over pi of y minus 1. Okay, so this is less than or equal to the sum from j equals 2 to the size of x of the absolute value of fj of x, fj of y, lambda star to the t. Okay, so the point here is we're taking the absolute value, so we're using this expression, no, actually I guess this one. So we're taking this one and we're saying, let's replace lambda j by lambda star. That'll just make the absolute value bigger. Right, so actually this is the absolute value, right? So we're going to making it bigger by replacing each lambda j by lambda star. And then we also have this. Okay, so here I haven't used Cauchy-Schwarz yet. I'm just saying the absolute value of the sum is less than or equal to the sum of the absolute values. But then this, okay, now we use Cauchy-Schwarz to say that this is less than or equal to, okay, well, I'm going to pull out a lambda star to the t from the sum, and then I can write this, I can get a sum from j equals 2 to the size of x, fj of x squared, and then the sum from j equals 2 to the size of x of fj of y squared, and all of this to the 1/2. Okay, so that's by Cauchy-Schwarz. Okay, also, we can write pi of x as this delta x, so pi, right? If you write this out, you're going to get like a sum of, I guess it'll be a sum over, okay, maybe I'll just write it out. What is this? This is like the sum over y in x of delta x of y, delta x of y, pi of y. Okay, but then this is like 0 unless x equals y, and then you get 1 times 1 times pi of x. Okay, so it's that. Okay, but now the point is we have this way of expanding this delta x in terms of, where did I write this? We have this way of expanding it like this. So we can write delta x as the sum from j equals 1 to the size of x of fj of x, pi of x, fj. So pi. Okay. Okay, so here we can rewrite this as pi of x squared times the sum from j equals 1 to the size of x of fj of x squared. Okay, so that's because you can use, yes, okay, you can pull out a pi of x squared from here, right? Pull out a pi of x, pull out a pi of x, and then what you're left with is the sum from j equals 1 to the size of x of fj of x fj. And I guess, okay, we're supposed to use, okay, yeah, maybe I'll say, like, we're using the fact that the fj's are orthonormal with respect to this pi inner product. Okay, so where we use the fact that this basis is orthonormal with respect to this inner product with the pi. So that's allowing us, okay, again, we pull out the pi of x and the pi of x to get the pi of x squared, and then we have this sum of fj of x fj, fj of x fj. And so if you pair them up, like if you expand the sum into some big sum, you're only going to get a term where, like, you have fj matching with fj, and then you're just getting fj of x squared as your contribution. Okay, so then finally, what does this mean? Okay, so pi of x is equal to pi of x squared times this. So if we take the sum from j equals 2 to the the size of x of fj of x squared. Okay, so that's just this sum, except I dropped the first term. So this is going to be less than or equal to the sum with the full thing, because the first term is like 1. And, well, okay, maybe I'll just say this is equal to pi of x inverse minus 1, right, just by that. And then, okay, this is less than or equal to pi of x inverse, of course. Okay, and then finally, we can say this absolute value p to the t of xy over pi of y minus 1 is less than or equal to lambda star to the t. Right, so I want this is less than or equal to lambda star to the t. Okay, and then the point is this sum, right? We have this sum basically, for x and for y, and then we've gotten an upper bound on this. Like this sum is at most pi of x inverse. This sum is at most pi of y inverse, and then we have to the 1/2. So this is at most pi of x inverse pi of y inverse to the 1/2. And then this is less than or equal to lambda star to the t divided by pi min, because pi min is just the minimum possible value of pi of some state. And so, like if you replace pi of x with pi min here, and you replace pi of y with pi min here, then the whole thing is going to go up. Right, you're decreasing the denominator, so yeah, everything gets bigger. So we have that. And then, okay, well, what is this? Lambda star is just 1 minus the absolute spectral gap. So this is 1 minus gamma star to the t over pi min. And then this, we can just estimate 1 minus lambda, 1 minus gamma star to the t as e to the negative gamma star t divided by pi min. Okay, and then now we can say d of t. Okay, so our d of t is less than or equal to 1/2 this d2 of t. So this follows from one of those, I guess I've erased it by now, but one of those diamond or double diamond things that I had earlier with the relations between the dp of t things. So one of them gave us this, and then another one told us that this is equal to 1/2 the square root of this. So it's the max, this is the max over x at x of q2t of xx minus 1. Right, so we said that like dt, or d2 of t squared was this thing. And this is less than or equal to, so now, okay, this, what is this thing? Well, we're going to get an upper bound from here. So we get square root of e to the negative 2 gamma star t over pi min, because, okay, so it's exactly this bound here, except with t replaced by 2t, so I want the 2t here. And then finally, I can pull this out of the square root, and I get e to the minus gamma star t over 2 root pi min. Okay, and then we wanted to say this, and I guess I'll just say that like that follows from sort of inverting this. Yeah, so maybe I won't go through it, but the point is like once you have this inequality with the d of t, you can just say what that means in terms of the mixing time, and you end up getting this. So we have an upper bound for the mixing time in terms of the relaxation time. Let me also state a theorem giving a lower bound for the mixing time, also using the spectrum of P. And any questions up to here? Okay. Yes, I don't know, maybe I'll have time to, yeah, this is fine. Okay. Theorem. So suppose P is irreducible and aperiodic, and let's suppose we have some eigenvalue lambda that's not equal to 1. Okay, so this is an eigenvalue of P. Then we have this lower bound for the mixing time, T max of epsilon. This is at least 1 over 1 minus the size of lambda minus 1 times log of 1 over 2 epsilon. Okay, so first, the theorem is trivial if lambda is 0. Because if lambda is 0, this is 1 minus 1, and so you're saying the mixing time is non-negative, which is obvious. So assume lambda is not 0. Okay, so let's say, so lambda is an eigenvalue, so there's some eigenfunction, let's call it f. So suppose Pf is lambda f. Okay, then, I think, okay, so the point is e pi of f is 0. I think maybe I stated why this is true at some point, but like the point is that, okay, what is this? It's the sum of, it's the sum over all the states x of f of x, pi of x, and I guess if you multiply by p, then you end up getting an equation telling you that this is 0, so that this is 0. So the absolute value of lambda to the t f of x, this is the same as the absolute value of p to the t f of x, which is the sum, it's the absolute value of the sum over y and x of p to the t of xy f of y. And then this, okay, we can write this, yeah, okay, let's write it this way. It's the sum, or the absolute value of the sum over y in x of p to the t of xy f of y minus pi of y f of y. Okay, and why is that? Well, in this sum, the second term is actually 0, right, because of this. So this 0 thing here is the sum over all y and x of f of y pi of y. So that's 0, so that's why these are actually the same thing. Okay, but then here I can upper bound this, so I can push the absolute value into the sum. I can say this is less than or equal to the sum of the absolute value, and then when I push the absolute value in, I can pull out I can upper bound f of y with its infinity norm. So I'll say this is less than or equal to the infinity norm of f sum over y in x of p to the t of xy minus pi of y. Okay, so again, just pushing the absolute value in, and then upper bounding f of y by the infinity norm of f. And okay, what is this? Well, this is just 2 times the infinity norm of f times d of t. Because d of t is exactly this, like, it's exactly 1/2 of this sum. Okay, almost out of time, but I think I can finish this. So choosing x such that the absolute value of f of x is equal to the infinity norm of f. Okay, so we can do this because x is a finite state space, so it must attain its maximum somewhere. And if we do this, we get that, okay, so from this, we end up getting that the absolute value of lambda to the t is less than or equal to 2 times d of t. Okay, and then from that, you can show that the absolute value of lambda to the t mix of epsilon is at most 2 epsilon. Yeah, so t mix of epsilon times 1 over absolute value of lambda minus 1 is at least t mix of epsilon log 1 over absolute value of lambda, which is at least log of 1 over 2 epsilon. Okay, so that's, so I guess this is just an inequality about log, and this is an inequality coming from here. And then if you rearrange this, you get what we want. So rearrange this and you end up getting